Morning, everyone. Today we are going to discuss about complete EDT architecture and its operations. So normally the EDT is used to reduce the tester time and test data volume. So we'll see how it is going to reduce. Basically, the architecture of EDT will consisting of three main components. First one is decomposer, compactor, nothing but a compressor and internal scan chains. That is a core. So these are called the internal scan chains and these are called the external scan channels. External scan channels. So if we clearly observe here, internal scan channels are two, internal scan chains, sorry, external scan channels are two, internal scan chains are many. So what is advantage of this one? Suppose if we have internal scan channels are two, each one is having the length of 100 flops. Each scan channel is having length of 100 flops. So if you convert those 100 flops into 10, 10, 10, 10 flops, each scan chain is having the 10 flops. So if you parallelly apply the clock for them, the help of 10 shift cycles, we can able to shift the data. Suppose here, external scan channels, if we have 100 scan flops means we require 100 clock pulses. Here you require only 10 clock pulses like that. Can able to reduce the tester time. So we will see with the example. As of now, the help of EDT logic, we can able to reduce the test time and test data volumes. Everything I will explain neatly. So the major components I told you, decomposer, compressor or compactor, internal scan chains are core. So decomposer consisting of a ring generator, phase shifter, compressor consisting of XOR tree and masking logic. So what is the use of this masking logic? Means this masking logic, if any scan chain, internal scan chain is propagating X, so with the help of this masking logic, we can able to block it. This masking logic consisting of an AND gate connected to mask hold register. Mask hold register is driven with mask shift register. So all these are pulsed with EDT update and EDT clock. So with the help of EDT update and EDT clock, we can able to control this masking logic. So with the help of this XOR tree, we can able to connect this more number of internal scan chains to less number of external scan channels. So compression is happened through with the help of this XOR tree. So if you come to the decomposer, so decomposer we have a ring generator and phase shifter. So ring generator will generate the pseudo random patterns. So those patterns are applied to phase shifter. So this phase shifter is randomize the patterns which are generated by the ring generator. Why? Because the ring generator generated patterns are having the linear relationship. So to overcome that linear relationship, so we'll go with the phase shifter. Actually, it has and some XOR logic. XOR logic. So with the help of that, we can able to randomize it. And also this phase shifter will connect it to the internal scan chains. So with a single pattern, we can able to we can pass this single pattern to the multiple scan chains to detect the more number of faults. So with the help of ring generator. So here the advantages of EDT logic are it will reduce the number of ports, reduce the tester time, so reduce the test data volume, compressed version of test pattern data. So the limitations is only one limitation is that the area overhead. Area overhead because of the decomposer, compactor and masking logic. So extra area is added to the logic. So more control needed over the EDT signals like EDT update and EDT clock. So we'll see it why these are more controllable. So EDT clock, EDT update and EDT clock. So these two will not, EDT clock will not be pulsed during the capture phase. Next one is components of EDT. EDT decomposer. So decomposer, as already I told that decomposer is consisting of ring generator and phase shifter. So ring generator will generate the random pattern. The output of the ring generator is connected to internal scan chains through the phase shifter. The phase shifter consisting of XOR logic, which provide the more randomness and drive the more number of scan chains. So it is going to drive the more number of scan chains. Told you that there is ring generated patterns. There is a linear relationship. So to avoid that one, we should have a phase shifter. So it will randomize the pattern. So linear relationship gets be cancelled. And the next one is compressor. So consisting of masking logic and XOR tree. Compressor consisting of masking logic with AND gates and XOR tree and pipeline flops. So pipeline flops is increase the speed of operation. Each XOR tree is XOR gate is connected to pipeline flops so to speed up the operation. So to block the X propagation of the scan chains, AND gates are used as a masking gates. So one input of AND gate is connected to internal core scan chain and other input of AND gate is connected to the masking logic. Yeah, here he explained that the first input of AND gate is the output of the scan chain and the second input of AND gate is controlled by masking registers and decoders. So decoder gives the value of 0 if any scan chain output is X, otherwise it gives 1. So as we know that if one input of AND gate is 0, then automatically the output of AND gate will become 0. So that like that, it is going to mask the particular scan chain which is propagating X. If any scan chain output is X, the particular AND gate output is 0. This way propagation of X is blocked. XRT is used to compress the several scan chains data and finally it gives less test data volume to the scan channel outputs. Scan channel outputs are connected. The pipeline pops are added in between the XR gates to increase the data transfer rate. So pipeline pops are used to increase the data transfer rate. So this is a EDT. This is a EDT bypass. So suppose these are the external scan channels. These are the external scan channels. If any problem occurs between the decomposer, compactor, and the core, so there is a connectivity issue. So EDT logic is not working. There is scan chain failure is going to happen in such a case. So if you want to test this normally, in such a case, we will go with the EDT bypass logic. What it will do? It will bypass the decomposer and the compactor. So it will uncompress the compressed scan chains. So these are the compressed scan chains. So it will uncompress it. So if you see, this can be EDT bypass logic can be implemented with the two multiplexer here, this one and this one. So if EDT bypass is 1, so it is connected like this, you see here, and it will goes to the this external scan. So normally this is compressed with 1, 2, 3, 4 flops. 1, 4, 1, 2, 3. 3, 4 is a 12 flops. So if you go with bypass logic means we require a 12 clock cycles. So if you haven't used the bypass logic means with the help of 4 clock cycles we can able to drive all these chains. Okay, right. So if it is 1, so this is connected like this 12 flops, and this is also connected like this 12 flops. Okay, external scan chain. So the function of this EDT bypass is that it is going to convert the compressed scan chain into the uncompressed scan chains, and also it will bypass the decomposer and compactor logic. Yeah, these are the EDT signals. So this is the most important EDT signals. So we have a scan enable, scan clock, EDT update, and EDT clock. So these two are the important. EDT clock is important. You should not share the EDT clock pin with any other pin. So if you share, we will face some issues. I will explain my next upcoming slides. So you see here. So we have load unload, shift, capture, load unload, and shift out. Shift in, capture, and shift out. So load unload. So during the load unload, so EDT clock and EDT update is going to be pulse. EDT update is high and EDT clock is going to be pulse, so that all data which is having the data that is shifted out, and a new data is loaded into the scan chains. So EDT update is high and EDT clock is pulsing during the load unload. During the shift, EDT update is zero. EDT update is zero during the shift, and the EDT clock is pulsing and scan clock also pulsing. So the data is loaded into the scan chains. So during the capture, see here during the capture, uh, EDT clock should not pulse. Only scan clock is going to be pulse. So when the scan clock is pulsing, so the functional data is loaded. Capture phase, the functional inputs are loaded into the logic block. And now you see here, if EDT clock is going to pulse here, so that whatever the data which is loaded, that is replaced with the new data scan chains, new data, so that the previous data is skipped out, and we can't able to detect the patterns which is we are going to detect with the previous data. So because if EDT clock is pulsing during the capture phase, so again load unload and EDT clock is pulsing, and EDT during the shift, EDT update and EDT clock also pulsing. So here, so this we should remember that during the capture, EDT clock is not going to pulse. EDT clock is pulsing, then the scan chains are loaded with new data, and the previous data which is loaded in the scan chains, which is intended to detect some faults. So we are going to miss it out if EDT clock is pulsing during the capture phase. Yeah, here he is explained EDT clock signal should not be pulsed in capture phase. The reason for that, EDT clock is pulsed in capture. The new data will be pumped into the scan chains. The previous data will be replaced with the new data. So the previous data which is intended to detect the particular fault, that fault cannot be detected. So EDT update signal is used to reset the, EDT update signal is used to reset the LFSR flags which are there in the decomposer. EDT update signal must be high for one clock cycle load unload phase. So the previous data will be completely shifted out and new patterns will be loaded. Yeah, both the EDT clock and EDT update signals are pulsed in load unload phase. Yeah, yes, already I told that with the help of EDT logic, we can able to reduce the test time and test data volume. So we'll see with one example how we can able to reduce the test data and test data volume. So here the number of shift cycles per pattern is nothing but length of the scan chains. So length of the scan chain. So here the length of the scan chain is 50. There are 50 flops in the scan chain, internal scan chain. So it is without EDT, external scan channel. There are 50 flops. So number of patterns are 20. So scan clock time period is 1 nanosecond. So test time can be number of patterns, number of shift cycles per pattern into test clock. So here the number of patterns are 20, number of scan chain length, number of shift cycles per pattern is 50, and scan clock time period is 1 nanosecond. So without EDT, we can able to complete the operation. Without EDT logic, we can able to complete the operation with 100 nanoseconds time period. So with EDT, the number of patterns are 25. The patterns are, we increased just patterns. Patterns are increased, and scan chain length is reduced to 25. So each scan chain having the length of 25 flops. The scan clock time period is same, 1 nanosecond. So here this external scan chain length is 50 and internal scan chain length is 25. If you see here, so the test time is number of patterns, number of shift cycles per pattern 25, and the scan clock time period is 1. So almost is 625 nanoseconds. Almost half of the time is reduced if you go with EDT logic. Yeah, test data volume. So test data volume, the formula for test data volume is number of patterns, number of shift cycle per pattern into number of external scan channels. So you see here external scan channels. So here the number of patterns are 20, scan chain length is 50, number of chains are 5. So you see test data volume is without EDT 20 and the chain length is 50 and the chains are 5. External scan chains are 5 channels. That is channels. External scan channels are 5. So with the help of 500, because it is test data volume is 500. So with EDT, number of patterns, just increased the patterns at 25. Chain length is 25 only. The number of channels are 5. So you see here the help of if you go with the EDT, the test data volume is 3125, almost half. So if with the EDT, test time and test data volume will be reduced. The two example, we can say that test time and test data volume is going to be reduced with the help of EDT. So here we will see the X blocking. So as already I told that with the help of masking logic, we are going to block the scan chains which is propagating the X. So if you see here, this is one scan chain, and this is other scan chain. Two scan chains. So here it is propagating X. With the help of this, we will get a external channel output is X. So to avoid that one, in this example, the length of the first one is 8 and the length of chain 2 is 3. Here the last, so it is not related to that one. Yeah, X blocking. That is X blocking. Yeah, you see the scan chain masking. So this is a right one. The scan chain masking. So how we can able to mask? So if these two you see here, this blocking, this is having X, this is having X and this is having 1 first bit. So this scan chain is propagating X and this is not propagating X. This is having some value. So we have to block this particular scan chain. For that, the masking bit of this particular AND gate is 0. So that this get masked and this chain gets propagated to the output. So like this, we can able to mask. Yeah, here for this one, previous slide, I have given explanation. So handling of scan chains to different length. So this is a scan chain 1 having some length and this is scan chain 2 having some length. So here its length is 3 bit and its length is 8 bits. So what we have to do? We have to append these bits of previous. So I will explain that one. Yeah, in the above example, length of this scan chain is 1 is 8 and the length of this scan chain 2 is 3. So here the last 5 bits of the scan chain 2 is filled with the first 5 bits of the next pattern. Here the scan chain which is having the length of 3 is filled with the first 5 bits of the next pattern. Then XOR it together. This procedure is applicable to all the patterns but not to the last pattern. In atpg, empty bit positions are filled with excess. So this one. So these bits are next pattern, first 5 bits. These bits are next pattern, first 5 bits are filled. So that these two scan chains are gets balanced. So why we have to balance the scan chains? Means to reduce the tester time. So dummy cycle. So if to reduce the tester time. So next one is low power test. So what is the purpose of low power test? So we have the two types of low power pages. Low power shift and low power capture. Actually, to reduce the shift power, we have a clock gating logic. Uh, sorry, Q gating. To reduce the shift power, we have a Q gating. To reduce the capture power, we have a clock gating. So we have it. So anyway, we will discuss here. So how to reduce the shift power, low power shift? So low power shift in many of the test patterns contains the X values which are not intended to detect any fault. So if a scan chain is having X value, it is not detect any fault. So only some of the bits contains ones and zeros. These bits will detect some specific fault. So generally Generally, the X values are filled with ones and zeros randomly. So switching is more and power consumption is more in this case. Suppose if you have an X values, the ATPG tool will replace with ones and zeros. So if we replace the ones and zeros means 0 to 1 and 1 to 0 switching activity is more. Suppose if we with the help of low power shift technology, we can able to replace this ones and zeros with the zeros. So thus we can able to reduce the switching activity. So the low power, the shift power can be reduced. So in low power shift, the power controller adds a constant zero values in place of X. So the switching activity will be reduced and the power consumption will be reduced. For example, if a pattern is having 10 XX11, this case X's are replaced with randomly with 1 and 0. So 3 times switching will be done because 1 to 0, 1 to 0 and 0 to 1, 0 to 1 and 1 to 0. Again 1 to 0, 0 to 1 and 1 to 0. Again see 3 times switching activity has to be done. So if these are replaced with the constant zeros, these two are constant zeros, the number of switching transitions will be minimized and thereby reducing the power. So we enable the power controller. This is important. We enable the power controller logic in EDT phase and constrain the power shift enable value is 1 in atpg. So low power capture, it uses the clock gators which are already available in the design. The clock gators provide the clock whatever the portion of the design needs the clock. It turns off the clock where it not be needed. So power consumption will be reduced. So last pattern. So we see here last pattern handling of last pattern as already accept the last pattern. So remaining scan chains. So what are the for if you go for balancing, so we should add with the zeros and ones. So if you see here, so to block an X propagation, so for this particular bit both are one. So this one is one and this is one. So this particular bit and these both are propagating X. So this will be 0 first one. Automatically this will propagate. Last pattern handling, the empty bit positions in the unbalanced chains are replaced with the last pattern bits again. Only last pattern bits again. Again the last pattern bits. So if see here last pattern bits are 1x0 1 1x0 1. So handling of last pattern bits again. This example length of the he has explained and masking code for that particular one is also explained. So this is all about EDT. So if you like this video, please share and subscribe.